Unit 3.1 covers special prokaryote topics, the Gram stain, biofilms, and endospores. Last week you learned about the structures of prokaryotes, both the external and the internal structures, and this week in Unit 3.1 we are taking a look at some of the real-life applications that the organisms put to these particular structures, as far as some real-life applications that we as scientists can apply to these cellular structures. The first special topic is the Gram stain. Most of the section of the Gram stain is a self-study, so be sure that you complete those self-study sections. If you look at the PDF for Unit 3.1 in D2L, you'll be able to check a lot of what you have filled out in your self-study section. Anything that's not found on the PDF should easily be able to be found in the textbook. The picture that you see here is Dr. Hans Christian Gram. He's the physician who experimented with stains and dyes, trying to visualize microorganisms under the microscope. As you know from looking at wet preps, an organism under the microscope is very hard to see in detail because it really isn't colorful. But by drying the organism on making it stick to a slide with heat, we can apply different stains and chemicals to actually visualize some of the morphologic characteristics of the organism, and that's what Dr. Gram was trying to do. I'd like you to focus your attention on just one particular aspect of the Gram stain and as it relates to the structure of bacteria. Now in the original PDF for Unit 3.1 you'll see a lot of slides that pertain to the four-step Gram stain process, but I think that it's a lot more interesting and a lot more fun to do the Gram stain in a laboratory, and you will be doing that hopefully this week if the weather cooperates. So for lecture, what I'd like to emphasize for you is that the basis of the Gram stain is that the color of organisms changes depending on the differences in the structures of the cell walls of the organism. So looking at the photograph, you can see gram positive cells in the top photograph, and they stain purple. You can see them appearing as little clusters, sometimes some diplococci in that photograph. Below that are gram-negative organisms that stain as pink in a Gram stain. And here's how the Gram stain works. Different cell walls react to the stains and the chemicals in the Gram stain in different ways. Because the Gram stain is a step-by-step process, the application of chemicals and dyes from one step to another is influenced by that cell wall. Thicker cell walls retain or hold on to that crystal violet dye. Thinner cell walls, as they go through the entire step-by-step Gram stain process, cannot hold on to that crystal violet dye, and it's necessary to actually counter stain them with another dye or stain called safranin. In those instances, these gram-negative organisms that have lost their ability to hold onto that purple crystal violet stain will pick up the pink safranin stain. So if you look at a Gram stain of organisms on a slide, organisms that are gram-positive with thick cell walls stain purple, organisms that are gram-negative with thin cell walls stain pink. So I hope you had an opportunity to think about the answer to these two questions in your self-study. Can the Gram stain be used to diagnose the flu? The answer to that is no. The flu is caused by the influenza virus. A virus is not a bacteria. A virus does not have a cell wall. A virus is just a little piece of DNA or RNA with a protein coat. So it is unable to pick up the stains used in the Gram stain. Can a Gram stain be used to diagnose tuberculosis? Again, the answer is no for a different reason. Mycobacterium tuberculosis is a bacteria. It is a microorganism. But remember that mycobacterium have a very waxy cell wall, and the waxes in the cell wall resist the stains and chemicals that are used in a gram stain. So there's a special stain that has to be used for mycobacterium. The specialist topic number 2 is biofilm formation. Be sure to complete the self-study section for biofilm formation, and you can use the Unit 3.1 PDF in D2L to check some of your answers on page 28. For the answers to for the responses to other questions, you can refer to your textbook. The last topic in Unit 3.1 is the formation of endospores. And you can see in this photograph the image of several endospores, and they're indicated by the little black arrows. The endospores themselves are located inside of that clear pink capsule. That thick protective capsule is what allows the endospore, which is inside the capsule, to survive under very harsh conditions. And some scientists with a lot of imagination like to describe the particular endospores that you're looking at as having a safety pin appearance. And these are endospores of the genre, usually Bacillus or Clostridium. And you had the Bacillus anthracis as one of your pathogens of the week several weeks ago. If you'd like to hear a song about endospores, just click on the photo in the D2L PDF, and there are a lot of songs about parts of bacteria, actually, and this is one I found that I thought was a little amusing. Might help you remember something about endospores. It's important for you to watch the video about endospore formation also, and you can do that by clicking on the PDF in D2L. There are also links to that song and the video on endospore formation directly in the Unit 3 section of D2L. Endospores are considered to be the most resistant of all life forms, and you're going to find out why as we go through these slides. The purpose of an endospore is to allow an individual bacteria to survive in conditions that really are not compatible for the typical life of that microorganism. Your textbook calls endospores the ultimate survivors. Endospores are able to exist in soil, in dust. It could be dry soil, it could be very wet soil. And because they are environmental organisms, they are often picked up by open wounds. They are also quite commonly infecting puncture wounds. For example, if a rusty nail is lying on the ground and you step on the rusty nail and it deeply punctures your skin, endospores that are carried on that nail, picked up by the soil, could enter your nice, warm, moist body deep down inside where there are lots of nutrients, and those endospores would then convert to the living, make you sick, vegetative version of their former selves. The formation of endospores is a cyclical process, and so I have given you a diagram to look at here. I would like you to first focus your attention on the right-hand circle of this diagram, where the caption is germination, the vegetative cell. A vegetative cell is that living, growing, make you sick form of the microorganism. And that might be a little bit different from what you think about when you think about a vegetable. When I think about a vegetable, I think of someone who's a couch potato, who sits on the couch and watches television and really isn't very active. Sometimes, unfortunately, people who are in a coma or unresponsive might be referred to as being a vegetable. However, for a microorganism, it's completely the opposite. The vegetative form of a bacteria is the living, growing, make you sick form of the microorganism. A vegetative cell becomes an endospore, as represented in the left-hand blue circle, through the process of sporulation. So a vegetative cell undergoes sporulation to form an endospore. When conditions are right, when they're warm or they're moist or nutrients are available, the endospore undergoes germination to form a vegetative cell. Let's look more closely at the formation of the endospore itself. Remember, endospores are formed during the process of sporulation. The result of sporulation is a dormant microorganism called an endospore. Sometimes your textbook uses the word spore interchangeably with endospore, so you have to look out for that. Some significant characteristics of the endospore are as follows. Endospores form when bacteria find themselves in adverse conditions, conditions which really would not support their living, growing versions of themselves. It might be extremely dry, there may not be enough nutrients available, it might be very cold when a bacteria prefers to be warm, or very warm if a bacteria prefers to be cool. One of the key characteristics of endospores, what allows them to survive for so long, is that coat that they grow, that you're going to learn about soon, allows them to withstand extremes. That could be extreme heat, extreme cold, a very dry environment, and extremely harsh chemicals. Now let's look a little more closely at the germination process. During germination, a endospore becomes an active, vegetative, living, growing microorganism. Significant characteristics of a vegetative cell include the fact that it lives only under the optimal living conditions, and that it is in the vegetative state that the bacteria can divide and multiply and form more and more and more of itself. That's the germination resulting in the vegetative cell means that the organism has the opportunity or the potential to become pathogenic. And if you remember that term, a pathogenic organism is one that can make you sick. So a endospore itself cannot make you sick because it's just sitting there with its super thick coat on, waiting to be able to convert to a vegetative cell. It's that vegetative cell that can grow and divide and cause disease. That's what makes a vegetative cell pathogenic. Let's look at a few details of sporulation. Remember, that's the formation of an endospore. We talked about conditions being deplete of nutrients. That's when an endospore forms from the vegetative microorganism. It's really important to know, and sometimes confusing to people, that one endospore forms from one vegetative microorganism. So the sporulation event is not a reproductive activity. One endospore from one vegetative cell. That sporulation process takes approximately 6 to 12 hours, depending on the organism and depending on the kind of conditions that it's existing under. Before we spend time looking at this slide and the steps in sporulation, I'd like you to make one change in your notes, please. there's a sentence in your notes that says, if given a diagram such as figure 4.22, be able to label the steps during which a vegetative cell converts, etc., etc. I'd like you to change the word label to locate. I don't expect you to actually label the steps, but if I ask you to find one of the steps by name, if I give you the name of the step, you should be able to find it on figure 4.22. Now below you see steps 1 through 5, which are a summary of the steps that occur during the sporulation process when a vegetative cell becomes an endospore. And we're going to look at those steps in detail in the next few slides. Before looking at the text, let's take a picture, or let's take a look at the diagram. You will see that there are 5 boxes, fairly large white boxes, numbered 1, 2, 3, 4, 5. You also see a lot of tiny little yellow circles that also have numbers in them. Numbers 1 through 5 are Nancy's steps in the stages of sporulation. It's just a little bit shorter, a little less detail than the textbook steps. So we're going to discuss sporulation in just 5 steps. So let's start with step 1. Step 1 shows you a diagram of a vegetative, living, make-you-sick cell. And as the vegetative cell moves from step 1 to step 2, it commits to becoming a sporangium. And a sporangium is a term used for a bacteria that is absolutely committed to forming an endospore. There's no turning back once the vegetative cell commits to becoming an endospore. In step 3 of this diagram, you can see on the left that a little 4 spore is beginning to form after the chromosome has duplicated back in step number 2. That 4 spore is the precursor to the endospore. Let's look at steps 4 and 5. In step 4, the cortex, or the thick protective coats around the 4 spore, begin to form. And they are represented by the thick, pale, yellow or tan coating around the 4 spore. And then if you look at step number 5, at that point, the 4 spore has actually become an endospore, and the dead sporangium has sort of shriveled up and fallen away. So at this point there, at step number 5, you are looking at the endospore, the dormant version of that very same vegetative cell that you started with in step number 1. Now we've completed our discussion of the stages of sporulation. We're now moving on to the stages of germination. And as you remember, germination is the formation of a vegetative cell from an endospore. Or in this diagram, you can see that the word has been shortened to spore. Now I think this diagram is kind of interesting because if you look at the spore, if it's a face of a clock, it would be in the number 9 position, and you look at the vegetative cell in the 12 o'clock position, there's just one other image between the spore and the vegetative cell. And that one little tiny image is supposed to represent all the steps of germination. So I have made my own diagram, which you're going to see in a few slides from now, to better represent that germination process. But this is where the germination occurs, right here on this slide, between the step of the spore being formed and the step of the vegetative cell being formed. In looking more closely at the germination stage, you can see that there are a few special characteristics that you need to know about. During the germination process, the endospore form of the organism finds itself in a nutrient-rich environment with just the right amount of moisture, and the vegetative cell is then beginning to form from that endospore. And just like in sporulation, in germination, one vegetative microorganism forms from one endospore. There's no division of cells here. It's just a conversion of the cell from a endospore stage to endospore state to a vegetative state. It's not a reproductive activity. The germination stage typically is faster than the sporulation stage, and scientists estimate, depending on the organism, that this germination stage takes between 1 and 2 hours. On the slide following this one, we will be looking at Nancy's diagram of the germination stage. It's not figure 4.22, it's Nancy's diagram. If you were given a diagram such as the one on the next slide, you should be able to point out which step is being described. And the steps are listed there, 1 through 4 below. And we'll look at each step individually on the next slide. Because germination is the formation of a vegetative cell from an endospore, let's start with the endospore. It's the dark blue circle in position 9 o'clock position on this diagram. And if you follow around clockwise in the circle, you can see the stages of the formation of a vegetative cell from an endospore, the stages of germination. When an endospore encounters water and some germination agent, probably a nutrient of some sort, perhaps a temperature change, the enzymes within the endospore begin to emerge. The endospore begins to form these enzymes, and those enzymes are responsible for digesting that thick protective cortex that surrounds the endospore. Once that core is exposed to water, once the cortex falls away, the core is lying there naked, it's exposed to water. The core takes up the water, it rehydrates and begins to absorb nutrients, and at that point the core, which at one point was the endospore, becomes a vegetative cell. And that's the last step in the germination process there at the 7 o'clock position. Now you can see in the pale gray text that to move from that vegetative cell to the endospore, the process that occurs is that of sporulation, which you learned about just a few slides ago. If you have any questions about Unit 3.1, please call me or email me so I can clarify those for you. And thank you very much for your patience and understanding during this snowstorm. And I am interested in your feedback about both the self-study section and these recorded lectures. Have a good night.